Hello, and welcome to our video on activation energy. Imagine waking up on a day when you have lots of fun stuff planned. Does it ever happen that, despite the exciting day that lies ahead, you need to muster up some extra energy to get yourself out of bed? Once you're up, you can coast through the rest of the day, but there's a little hump you have to get over to reach that point. The activation energy of a chemical reaction is kind of like that hump you have to get over to get yourself out of bed. Even energy-releasing, exergonic reactions require some amount of energy input to get going before they can proceed with their energy-releasing steps. This initial energy output, which is later paid back as the reaction proceeds, is called the activation energy and is abbreviated EA. In chemistry and physics, activation energy is the minimum amount of energy that must be provided for compounds to result in a chemical reaction. Almost all the chemical reactions require some activation energy to go forward. Therefore, it's important for students to know what activation energy is. The activation energy, EA, of a reaction is measured in joules per mole, kilojoules per mole, or kilocalories per mole. Activation energy can be thought of as the magnitude of the potential barrier, sometimes called the energy barrier, separating the minima of the potential energy surface pertaining to the initial and final thermostatic state. Activation energy can be thought of as the magnitude of the potential barrier, sometimes called the energy barrier, separating minima of the potential energy surface pertaining to the initial and final thermodynamic state. For a chemical reaction to proceed at a reasonable rate, the temperature of the system should be high enough such that there exists an appreciable number of molecules with translational energy equal to or greater than the activation energy. The term activation energy was introduced in 1889 by the Swedish scientist Svante Arrhenius. Activation energy is defined as the minimum amount of extra energy required by a reacting molecule to get converted into product. It can also be described as the minimum amount of energy needed to activate or energize molecules or atoms so that they can undergo a chemical reaction or transformation. Why would an energy-releasing reaction with a negative delta G need energy to proceed? To understand this, we need to look at what actually happens to reactant molecules during a chemical reaction. In order for the reaction to take place, some or all of the chemical bonds in the reactants must be broken so that new bonds, those of the products, can form. To get the bonds into a state that allows them to break, the molecule must be contorted, deformed, or bent into an unstable state called a transition state. The transition state is a high energy state, and some amount of energy, the activation energy, must be added in order for the molecule to reach it. Because the transition state is unstable, reactant molecules don't stay there long, but can quickly proceed to the next step of the chemical reaction. In general, the transition state of a reaction is always at a higher energy level than the reactants or the products, such that EA always has a positive value, independent of whether the reaction is endergonic or exergonic overall. The activation energy shown in the diagram is the forward reaction, reactants to products, which is exergonic. If the reaction were to proceed in the reverse direction, endergonic, the transition state would remain the same, but the activation energy would be larger. This is because the product molecules are lower energy and would thus need more energy added to reach the transition state at the top of the reaction hill. An activation energy arrow for the reverse reaction would extend from the products up to the transition state. The source of activation energy is typically heat, with reactant molecules absorbing thermal energy from their surroundings. This thermal energy speeds up the motion of the reactant molecules, increasing the frequency and force of their collisions, and also jostles the atoms and bonds within the individual molecules, making it more likely that bonds will break. Once a reactant molecule absorbs enough energy to reach the transition state, it can proceed through the remainder of the reaction. The activation energy of a chemical reaction is closely related to its rate. Specifically, the higher the activation energy, the slower the chemical reaction will be. This is because molecules can only complete the reaction once they have reached the top of the activation energy barrier. The higher the barrier is, the fewer molecules that will have enough energy to actually make it over at any given moment. Many reactions have such high activation energies that they basically don't proceed at all without an input of energy. For instance, the combustion of a fuel like propane releases energy, but the rate of reaction is effectively zero at room temperature. To be clear, this is a good thing. It wouldn't be so great if propane canisters spontaneously combusted on the shelf. Once a spark has provided enough energy to get some molecules over the activation energy barrier, those molecules complete the reaction, releasing energy. The released energy helps other fuel molecules get over the energy barrier as well, leading to a chain reaction. Most chemical reactions that take place in cells are like the hydrocarbon combustion example. The activation energy is too high for the reactions to proceed significantly at ambient temperature. At first, this seems like a problem. After all, you can't set off a spark inside of a cell without causing damage. Fortunately, it's possible to lower the activation energy of a reaction and to thereby increase reaction rate. The process of speeding up a reaction by reducing its activation energy is known as catalysis, and the factor that's added to lower the activation energy is called a catalyst. Understanding the energy necessary for a reaction to occur gives us control over our surroundings. One example is fire. Our intuitive knowledge of activation energy keeps us safe. Many chemical reactions have high activation energy requirements, so they don't proceed without additional input. We all know that a book on a desk is flammable, but will not combust without heat application. At room temperature, we need not see how the book is a fire hazard. If we light a candle on the desk, we know we need to move the book away. If chemical reactions did not have reliable activation energy requirements, we would live in a pretty dangerous world. Activation energy depends on two factors. One is the nature of reactants. In the case of ionic reactant, the value of EA will be low because there is an attraction between reacting species. While in the case of covalent reactant, the value of EA will be high because energy is required to break the older bonds. 2 is the effective catalyst. Positive catalyst provides such an alternate path in which the value of EA will be low, while the negative catalyst provides such an alternate path in which the value of EA will be high. Note: activation energy does not depend upon the temperature, pressure, volume, concentration, or coefficients of the reactant. An exothermic reaction is a chemical reaction that involves the release of energy in the form of heat or light. These reactions are the opposite of endothermic reactions and can be expressed in a chemical equation as follows. Reactants leads to products plus energy. Thus, in an exothermic reaction, energy is transferred into the surroundings rather than taking energy from the surroundings, as in an endothermic reaction. In an exothermic reaction, the change in enthalpy, delta H, will be negative. Therefore, it can be understood that the net amount of energy required to initiate an exothermic reaction is less than the net amount of energy released by the reaction. When a calorimeter, a device used to measure the heat released by a chemical reaction, the net amount of heat energy that flows through the device is equal to the negative of the total energy change of the system. However, it's extremely difficult to measure or even calculate the absolute total of energy in a given chemical system. Therefore, the energy change, or the enthalpy change, denoted by delta H, is measured instead. The relation between the value of delta H and the bond energies of the reaction can be given by the following equation. Delta H equals energy used in the bond formation that yields products minus energy released when the reactant bonds are broken. Therefore, it can be understood that an exothermic reaction will always have a negative value for the change in enthalpy, i.e., delta H will be less than 0. For the measurement of the enthalpy change of combustion reactions, bomb calorimeters are very suitable devices. Activation energy for forward reaction, EA sub F. Activation energy for forward reaction. Endothermic reaction. Endothermic reactions are chemical reactions in which the reactants absorb heat energy from the surroundings to form products. These reactions lower the temperature of the surrounding area, thereby creating a cooling effect. Physical processes can be endothermic as well. Ice cubes absorb heat energy from the surroundings and melt to form liquid water. No chemical bonds are broken or formed. When a chemical bond is broken, it's usually accompanied by a release of energy. Similarly, the formation of chemical bonds requires an input of energy. The energy supplied or released can be of various forms, such as heat, light, electricity. Endothermic reactions generally involve the formation of chemical bonds through the absorption from the surroundings. On the other hand, exothermic reactions involve the release of heat energy generated from bond breakage. Chemical reactions which require substantial amounts of energy can be difficult to control. Increasing temperature is not always a viable source of energy due to costs, safety issues, or simple impracticality. Chemical reactions that occur within our body, for example, cannot use high temperatures as a source of activation energy. Consequently, it's sometimes necessary to reduce the activation energy required. Speeding up a reaction by lowering the activation energy required is called catalysis. This is done with an additional substance known as a catalyst, which is generally not consumed in the reaction. In principle, you only need a tiny amount of catalyst to cause catalysis. Catalysts work by providing an alternative pathway with lower activation energy requirements. Consequently, more of the particles have sufficient energy to react. Catalysts are used in industrial-scale reactions to lower costs. Types of catalysts. Positive catalysts. A catalyst that helps to increase the rate of reaction, or which supports the reaction to carry out quickly, is called a positive catalyst. Such catalyst decreases activation energy by accepting a smaller path, so the rate of reaction is increased. Negative catalysts, inhibitors. A catalyst that decreases or retards or helps in slowing down the rate of a reaction is called negative catalyst. It works by increasing activation energy by taking a longer alternative path. Biological catalysts are known as enzymes. When reactant molecules collide with each other at its highest energy point, an intermediate is formed which remains in equilibrium with the main reactant. If this intermediate complex has an energy equal to or greater than the threshold energy, then it will be converted into a product. Arrhenius developed his eponymous equation to describe the correlation between temperature and reaction rate. The Arrhenius equation is crucial for calculating the rates of chemical reactions and, importantly, the quantity of energy necessary to start them. In the Arrhenius equation, K is the reaction rate coefficient, the rate of reaction. A is the frequency factor, how often molecules collide. R is the universal gas constant, the units of energy per temperature increment per mole. T represents the absolute temperature, usually measured in kelvins, and E is the activation energy. It's not necessary to know the value of A to calculate EA, as this can be figured out from the variation in reaction rate coefficients in relation to temperature. Like many equations, it can be rearranged to calculate different values. The Arrhenius equation is used in many branches of chemistry. One of the best examples involves rolling a large stone up a hill. The initial energy you use to roll the stone up the hill is the activation energy. It's the hardest part of the process. But as you can see in the diagram above, once you get the stone over the top of the hill, the rest of the reaction takes place, and the stone rolls down the hill, propelled by its own momentum. This is a critical concept to understand when it comes to getting started on important tasks and being more productive. By efficiently reaching the activation energy threshold, you can quickly get started on whatever you're working on and use natural momentum to carry you through it until completion. From there, you can basically coast without having to overexert yourself. It's complete zen. One of the biggest hindrances to becoming productive is distractions. Research has found that distractions are at epic proportions, with the average time spent on a task being just a minute and 15 seconds before an interruption occurs. What's worse is that it takes over 25 minutes on average to get back into the groove after being distracted. So that's why I want to focus specifically on blocking distractions for this example. If you can develop a framework for keeping distractions at bay, you can lower the activation energy needed to complete tasks and stay on track. Every positive habit you try to form requires activation energy. The harder the habit is, the more activation energy you need to develop it. Once you get over the hill, things get a lot easier, and you can basically ride the wave of momentum. Although activation energy is a scientific concept, we can use it as a practical mental model. Returning to the morning coffee example, many of the things we do each day depend upon an initial push. Take the example of a class of students set an essay for their coursework. Each student requires a different sort of activation energy for them to get started. For one student, it might be hearing their friend say she's already finished. For another, it might be blocking social media and turning off their phone. A different student might need a few cans of Red Bull and an impending deadline. Or for another, reading an interesting article on the topic, which provides a spark of inspiration. The act of writing an essay necessitates a certain sort of energy, dependent upon the person. Getting kids to eat their vegetables can be a difficult process. In this case, incentives can be used as a catalyst. You can't have your dessert until you eat your veggies. It's not only a psychological play on incentives, it also often requires less energy than constantly fighting with the kids to eat their vegetables. Once kids eat a carrot, they generally eat one another, and then another, and another one. While they still want dessert, you won't have to remind them each time, so you'll save a lot of energy. The concept of activation energy can also apply to making drastic life changes. Anyone who has ever done something dramatic and difficult, such as quitting an addiction, leaving an abusive relationship, quitting a long-term job, or making crucial lifestyle changes, knows that it's necessary to reach a breaking point first. The bigger and more challenging an action is, the more activation energy we feel is required to do it. Our coffee drinker might crave little activation energy, a cup or two to begin their day if they're well rested. Meanwhile, it'll take a whole lot more coffee for them to get going if they slept badly and have a dull day to get through. Thank you for watching our video on activation energy, and have a nice day.